Hello everyone, and welcome back to the continuation of our Introduction to the Finite Element Method series. In today's video, we're going to be continuing talking about Chapter 4, which is development of beam equations. And we're going to emphasize today on something called distributed load. So let's get into it. Basically, what we're going to cover today is we're going to cover how to deal with distributed loads, and we're going to solve a problem and basically explain how to calculate the bending moment diagram. And with that being said, well, sit back, relax, and enjoy the show. Now, before I start with this video, I want to just quickly give some recommended reading for some examples, and basically in the book of Daryl L. Logan. I'm just gonna quickly glimpse over them. This example in example 4.2 in Daryl L. Logan, basically you have like node number 1, node number 2, node number 3, 4, and 5, which means you have element number 1, element number 2, 3, and 4. Of course, you need to apply boundary conditions later in the problem. So you have no movement here and no rotation, as well as no movement here and no rotation. So, and here you have no movement. So in the end, what I'm expecting is that after you dash your stiffness matrix, you would have 2 rows here, 1 row here, that's 3, and 2 rows here, that's 5. So you would have a system of 5 equations with 5 unknowns. That's what I expect. This example is interesting because it basically mixes both beams and springs. And the only thing that changes here is that when you assemble the stiffness matrix, you have a spring element, which is AE over L, 1 minus 1 minus 1, 1. So this will be taken into account in the problem. And I think here there was something about support settlement or something. So those are examples that are worthy glimpsing over and checking out. In today's video, we're going to be talking about something called distributed loads. So how do we deal with that? Well, the short story is we calculate an equivalent load or force. And those are readily available in tables and so on. The long story is like, how do I know? For example, look at this. This is a distributed load. How do I know that I can take the distributed load and calculate an equivalent load like this on the nodes? How do I know that? How do I know that those loads are correct? What gives? I mean, maybe I can make sense of this load, WL over 2 and WL over 2. This is basically the total load here, which is WL divided by 2. Maybe I can make sense of it, but what gives with the moments? Now, those are called fixed end moments, and there is a reason why they are equivalent from structures. You must remember this from your structures courses. But the long story behind it is basically that you're looking for the following. You have a distributed load W. This distributed load W is a function in X. In our case, of course, the W here, the load, is a function of X, and it's constant in this case. Of course, this definition works for everything. It works even for W's that kind of look like this, any arbitrary equation. You have a load W of X, and this load will cause work. So you have to calculate how much deflection you have and so on. So the integration of all the work, W capital, made by the load W small must equal the work done by all those forces because of something called the conservation of energy and work. Meaning that it must equal moment 1, I will call it, multiplied by theta 1. Moment 1 is the equivalent moment at node number 1, plus force 1 multiplied by deflection 1, let me call it U or V, whatever, plus moment 2 multiplied by theta 2 plus force 2 multiplied by U2. And in the book, in the reference book of Daryl L. Logan, you will see a long derivation for this forces, basically proving that those are the ones that you use. It's called moment equivalent method. The idea is being, what are my forces that have the same work as my distributed load? And that's what the idea is. How does this change the problem? It changes the problem because now you have 2 types of loads you need to sum up together. You have a total load, which is basically the loads on the nodes plus the equivalent loads, which means that in the end, when you say F and say equals K multiplied by D, the F that you are using actually here is the total F, which is the nodal forces, plus the equivalent forces. Which means that in fact, the real equation is F total equals K capital, the global structural stiffness matrix, multiplied by D. Now we know that F total equals F plus F0, so F plus F0 or F naught equals K multiplied by D. So you can find the nodal loads by basically subtracting F naught from both sides. And that's how this equation looks. This also works for local forces, by the way. Now, how do you use this? There is an example I'll explain today. So let's dive into the example. Now, that's an example I selected here. I'm assuming length of the span is 5 meters. The load is 20 kilonewton or 20,000 for unit purposes. And the section is 0.3.5 meters. And the elastic modulus is 20 gigapascals. We are talking about concrete. Now, of course, this is my problem. This is my problem statement. This is the solution, because we already know what the solution of a two-span equalish beam is, and those are all the values that we will check against. Of course, we know nothing of those, but it's good to have like a value to check against. And in the end of this video, we're gonna be drawing the bending moment diagram, or at least part of it, and the shear force diagram. Okay, so that's our problem. Fine. What do I do in the beginning? In the beginning, I need to find my force vector, like my F from the nodes plus my F from the equivalent loads. Now, the F on the nodes is nothing, because there are no nodal forces in our structure. There might be nodal forces, but today we don't have. The only force we had on our beam is a distributed load. So, of course, I need to calculate the equivalent force or the equivalent loads on the two edges of those elements. Of course, we have node number 1 here, node number 2 here, and node number 3 here. What happens if we basically put, for example, a nodal force here? Let's say we add a nodal force here and say this is 10 kilonewtons. How do I deal with this extra nodal force? Now, of course, this problem has no nodal force, but if it exists, then you have two options. Option 1 is to add a node and deal with it as a nodal force. So you add a node here, let's call it node number 4, and deal with this as being a nodal force. But however, the other option is to basically take your 10 kilonewton, destroy it, and calculate the equivalent forces on the nodes based on the 10 kilonewtons. And I am a fan of option 2. Of course, it's option 2, not option 1. My teaching assistant has messed up, it seems. I'm a fan of option 2 because adding any node to your structure immediately adds degrees of freedom and adds complexity to the solution of the stiffness matrix. So whenever I have and by the way, if you remember robot, you have seen that there is something called bar loads. Like there is a clear differentiation between a point load inside a bar and a point load on a node. The reason behind this is because they are using the equivalent work to find the equivalent nodal forces and deal with it like this. Okay, so we find our equivalent forces. You have a force and moment on the right side here and a force and moment on the left side here. You have a force and moment on, you have a force and moment on each end for each element. So at element number 1, you have the left end and the right end. And for element number 2, you have the left end and the right end. Of course, here you have a force which is WL/2 based on what we just explained here, those ones. So you can see here this is WL/2. Now why it's negative? It's negative because the equivalent force goes down and we know that the positive Y goes up. What about the equivalent moment? WL²/12, which is going clockwise. Now we know that the counterclockwise is positive, and that's the reason why you have a negative sign here. Furthermore, for this node here, you have equivalent forces from the left bar and the right bar, which add together. And you have a left bar moment and the right bar moment, which are actually opposite. And that's the reason why you have a 0 here. Similarly, for node number 3. Okay, now we have established our equivalent nodal forces. Going on with this now, we need to assemble our global stiffness matrix. Of course, we are pros in this, so we know that the local stiffness matrix of a beam is basically this. Of course, I'm assuming that you have seen all the parts of the previous videos of this video series. If you haven't, I will link the playlist here. Also, I'm assuming you have seen how we have derived our stiffness matrix using the direct stiffness method of beams, and this will be also linked on the top right. So we know that the stiffness matrix of an element looks kind of like this. And notice I wrote K local 1 and K local 2 are actually equal. The reason is because they have the same length and the same orientation and the same cross-section. Nothing changes. So that's correct. Which means in the end, K, if I plug this into MATLAB, gives me basically this stiffness matrix. You need to pay attention to the units here. E is 20 times 10 power 9. I'm using Newton per meter units here. And the inertia is 1 over 12 ph cube, as you know from your statics courses. So that's my local stiffness matrix. Now I'm going to use it to find the global stiffness matrix. Of course, we are pros, and I just did it quickly. But doctor, where is the transformation matrix? I remember you saying like T transpose KT or something. Where is this stuff? It's not here today because our beams coincide, luckily for us. So far, our beams' local coordinate, local axis, coincides with the global axis of the entire structure, and that's the reason why no transformation occurs. So we're basically pros, and we add all those elements together. You can see the influence of element number 1 being here, which is from node 1 to node 2. And you can see the influence of element number 2 being on the other side, which is influencing node number 2 and node number 3. You can see that this place is a place of overlap between those two elements. You can see this clearly. 0.6, I guess, plus, 0.6 here, plus 0.6 here, gives you 0.12, and so on. So there is overlap. That shouldn't be a surprise because they are interconnected at node number 2. So of course they would share this node and will be having overlap. Of course, now we have our finite element problem. You have the force vector, you have the stiffness matrix, and the displacement vector. Of course, I know some displacements because I have pins and rollers. At the pin, there is no displacement in y. At the other roller here, there is no displacement in y because take a look here. You have here no displacement in y at node number 1, no displacement in y at node number 2, and no displacement in y at node number 3. But you have rotation at node number 1, you have rotation at node number 3, and because of symmetry, you don't have rotation at node number 2, but that's a special case because symmetry, I cannot know this for sure for other structures, so the only things I know for sure, regardless of the structure and the size, is no movement in y here, no movement in y here, and no movement in y here. This is the only things I am 100% sure of. Of course, the question is, hey, I realize this is 0. Can I use this? The answer is yes, you can, but I'm not doing this. Okay, so the deflection at 1, 2, and 3 are zeros, which means I can slash and dash my first row, my third row, and my fifth row, and of course, group up the surviving remainders. So this FF basically is the force after we dashed and slashed all those lines, and the KK is the stiffness matrix after I dashed and sliced all those lines. And what remains here is to say that, well, our force vector, which is basically those two together, don't forget that, you have two, which makes sense. So if I had a nodal force here, I would add it together. So my total force here equals K multiplied by D, which means that I can invert K and left multiply by F to get D, which is deflection. I called it theta here because the only things that remain after dashing and slashing are thetas, and you can see the values. It makes kind of sense because how do I read those values? Well, that's my beam, and my theta here is negative, which means my beam has a tendency to rotate clockwise, which totally makes sense under a deflection shape that looks like this. This is 0 almost because it's symmetry. There shouldn't be no rotation at the center. And this is positive, indicating that the beam is rotating counterclockwise at this point, which is in fact the case. So I'm not surprised. Having the deflection, I can use it to find the forces. Please notice that the forces that you find are basically the summation here. So if I take my stiffness matrix K and multiply by the displacement vector D, I get this force, I get this vector. This vector is the force total. This vector is not the nodal forces and not the equivalent forces, but it's a mix and mash of two of them. Now, you can basically find the nodal forces by taking this entire vector and saying negative. So for example, F1y equals negative 12,500 Positive 5,000, because I mean negative 5,000 when you go to the other side becomes positive, is 37,500, which coincides with the result 3WL/8 from the reference. That's perfect. For F2Y, similar things apply, and you can see me do the same thing here. And for F3Y, that's kind of amazing. Now let the post-processing begin. This is where the fun starts. So now I want to post-process each element on its own. So I'm going to talk about element number 1 and then quickly skim over element number 2. So I want to find the local forces. How do I find the local forces? The total forces equals the local stiffness matrix multiplied by the local deflection matrix. I can go and find the deflection of element number 1 by looking at the degrees of freedom. Element number 1 is responsible for node number 1 and node number 2. So this is your displacement vector for element number 1. But wait, doctor, you should transform it from the global axis into the local axis. And you are right. And there is no transformation. Wait, what? Why? Because the beam is in the same orientation as the global matrix, as the global axis. So no transformation is necessary, which means I can use this vector as is for element number 1, and I can use this vector as is for element number 2. You can see me doing exactly that. I select my deflections for element number 1. I remember that the total force equals K multiplied by D. So if I multiply K, the local stiffness matrix, by D, the local displacement matrix, I get the local forces. Now, those are not the reactions. Those are not reactions. Those are nothing. So far, I need to remember that those values here are nothing. They are the summation of two things, F and F0. Now, I call this F1, which means the nodal local forces at node number 1, and those are the equivalent forces. Of course, the equivalent force is WL/2 here and WL²/12 here, which makes sense. And yeah, I can easily find F1 by basically taking this and saying negative. So you can see those are the values for F1. Similarly, those are the values of F2. And now let's the fun start. How do I draw the bending moment diagram and the shear force diagram? Well, to do this, I'm gonna draw, this is piece number 1, which is from node number 1 to node number 2, and that's piece number 2, which is from node number 2 to node number 3. Now, what do I know? The local forces at element number 1 are as follows. It is up 37,500 and no moment here, and here I have up 62500 for the force, and I have negative, which means I have a clockwise moment because negative of counterclockwise. Remember, the positive direction is counterclockwise moment, so I have a clockwise moment of 62500. Those are the local forces of element number 1. Going to element number 2, what do we have? For element number 2, I have a force here of 62500, and I have a moment here of also 62500 positive, so counterclockwise, 62500, and I have at point number 3 a force going up of 37,500 and a moment of 0. Great. Now, how do I draw the moment diagram? This is element number 1 again. Now, I need to remember, what is the positive sign convention for the moment and shear force diagram? For the moment and shear force diagram, the sign convention, if you cut and take the left side, is down and counterclockwise. And if you cut and take the right side, it's up and clockwise. So this local force, yes, it coincides with the positive bending moment diagram, positive shear force diagram, which means that the shear here is positive 37500. That's the shear force diagram value here. What about this? This goes up, but the positive shear on the right side goes down, so those are not equivalent, and that's the reason why this is actually the opposite direction. So 62500 is gonna be a negative shear of negative 62500. But doctor, wait, it's positive here, right? Why are you putting it negative here? Because positive means going up, but on the right side, the shear is positive if it goes down, so game over, it doesn't work. I need to say negative here. Of course, how do you connect those two things? You have a distributed load, and you learn from statics that the shear force diagram is the integration of the distributed load, so you know that it's gonna be a line. Okay, fantastico. So what about element number 2? I will just write it here, and element number 2 is from node number 2 to node number 3. It starts with a force 62500 going up, and you know that the positive goes up for the shear force diagram, so the shear here is 62500. Here you can see the force going up, 37500. You know that the shear for the right side goes down, so the shear value here is negative 37, I guess, 500, and you connect them with a line. Now, if you add those two shear force diagrams together, you get the original shear force diagram, and that's how you draw shear force diagrams. That's, of course, part 1. Part 2 is to draw the bending moment diagram. Now, I need to remind you again, the positive bending is basically the thing that makes a smiley face, and remember that the moments are counterclockwise positive. So this was 0, so no moment here. This was negative 62500, so clockwise moment 62500. And for element number 2, this was 0, and this was positive, so counterclockwise 62500. Now, how do those moments translate into the moment diagram for the two elements? This is element number 1 between node number 1 and 2, and this is element number 2 between node number 2 and 3. For element number 1, the left side moment is going to be 0, so there is no moment diagram here. That's perfectly fine because it's the first roller support or pin. And for the left side, you have a 2 here. Sorry, for the left side, you have a moment of negative 62500, so you have a clockwise moment, but it's counterclockwise positive, which means that the moment diagram value here is negative 62500. You connect them by a parabola that looks like this. Of course, I'm drawing the Hibla sign convention. In some books, the negative is down, the negative is up and positive is down. I'm drawing vice versa. It doesn't matter actually, it's just a sign convention. How do I find the maximum moment here? How do I do that? Well, this is where you go to your shear force diagram that you just finished and try find the point where the shear force is 0, because then you can find the point of maximum moment, because as you know, the shear force diagram is the derivative of the moment, and the moment is the integration of the shear force diagram, and that's span number 1. If you go to span number 2, you have node 2 and 3. Take a look at the moments in span 2. This is counterclockwise, but we know that it's clockwise positive on the left side, so you have negative 62500. And by the way, this and the shear are equal. That's just a coincidence. And of course, here you have the moment 0, so that's your moment diagram that kind of looks like this, goes up and down. To find the moment here, you need to find the shear where it is 0. Of course, if you add those two things together, you get this moment diagram and everything is fine. And well, that's basically everything I wanted to explain today. This is how you do an analysis using the finite element method. It's kind of cool, and you might even incorporate this for the Excel sheets that you use for your design. So that's basically everything I wanted to talk about today. Now, before I finish, I want to give a huge finite element method sized shout out to our dear channel members. Those are our contributor level members. And I want to thank them from the bottom of my heart, as their contribution helps me deliver more videos in time and more enthusiastically. Of course, if you're interested, you can join the ranks of members by clicking on the join button of the YouTube channel. We have 2 levels, helper and contributor. So if you can and you feel like it, then do it. If you don't, if you cannot, then no problem. Your subscription and viewership is more than enough for me. So once again, a huge shout out to our dear channel members whose name are going to be shown on the screen. I want to thank them very much for all the support they provide to the channel, as they allow us to provide more videos on time. Thank you very, very much. With that being said, I hope that you enjoyed the video, and of course that it was beneficial for you. If you have enjoyed the video, then please like, share, comment and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.